Have you ever wondered how computers understand our instructions? It's a fascinating process that bridges the gap between human language and machine language. We write code in languages like Python or Java, which are designed to be easy for humans to read and write. However, computers only speak in binary, a series of zeros and ones that represent electrical signals. This is where compilers come in. These powerful tools are essential in the world of programming. Compilers act as translators, converting our human-readable code into machine language that computers can execute. Without them, our high-level instructions would be meaningless to a computer. It's like magic, turning words into action. Imagine the complexity behind this transformation. Imagine writing a letter to a friend in English. You pour your thoughts and ideas onto the paper. Now suppose your friend can't understand English, but has a special dictionary that translates each English word into their language. This is similar to how compilers work. They read your code and use a special dictionary, known as a compiler, to convert it into instructions the computer can understand. This process ensures that your intentions are accurately conveyed to the machine. This translation process is essential for all the software we use every day, from simple apps on our phones to complex systems running on servers. Without it, modern computing as we know it wouldn't be possible. Section 2. Programming in the Dark Ages. Before compilers, programming was like navigating a maze in the dark. Programmers had to write code directly in binary, a tedious and error-prone process. Imagine writing a novel by only using zeros and ones. It was a time-consuming and difficult task, and even a small mistake could lead to hours of debugging. To make matters worse, they used punch cards to input their binary code. These cards had holes punched in specific positions, representing zeros and ones. A single program could require thousands of these cards. It's no wonder that early programming was considered a specialized field for only the most dedicated individuals. Section 3. The Queen of Code and her Compiler Revolution. Meet Grace Hopper, a visionary mathematician and computer scientist who transformed programming. She envisioned programming languages that resembled human language, simplifying the coding process. In the 1950s, she created the first compiler, a revolutionary tool that altered the landscape of computer science. Hopper's A0 compiler laid the foundation for contemporary programming languages. It liberated programmers from binary code, enabling them to write more comprehensible, debuggable, and maintainable code. This breakthrough democratized programming, making it accessible to a broader audience. Section 4. Inside the compiler's mind, a step-by-step guide. So, how does a compiler actually work its magic? This is a question that has intrigued many, from seasoned developers to curious beginners. It's a multi-step process, with each step playing a crucial role in transforming code into an executable program. Understanding these steps can demystify the process and make you a better programmer. Let's break it down into smaller, digestible bites. This way you can grasp each concept without feeling overwhelmed. First, the compiler reads your code character by character like scanning a grocery list. This initial phase is known as lexical analysis. The compiler identifies keywords, variables, and operators, grouping them into meaningful units called tokens. These tokens are the building blocks of your code. It identifies keywords, variables, and operators, grouping them into meaningful units. This is akin to breaking down a sentence into words and punctuation marks. Next, the compiler checks if your code follows the grammar rules of the programming language. This phase is known as syntax analysis. It's like checking if your sentences are grammatically correct. Just as a sentence needs proper structure, so does your code. Any syntax errors like missing semicolons are flagged. These errors must be corrected for the code to compile successfully. This ensures that the code adheres to the language's rules. Then, the compiler dives deeper into the meaning of your code. This stage is known as semantic analysis. This stage dives deeper into the meaning of your code. The compiler ensures that variables are used correctly, types are compatible, and logic makes sense. It's like making sure your instructions are clear and unambiguous. This step is crucial for the program to run as intended. Once all these checks are complete, the compiler translates the code into machine language, creating an executable program. This final step is known as code generation. And there you have it, a step-by-step guide to understanding the inner workings of a compiler. With this knowledge you can write better, more efficient code. Section 5. The Art of Optimization, making code faster and leaner. Once the compiler has understood your code, it's time for optimization. This step is like fine-tuning a car engine to make it run faster and more efficiently. The compiler analyzes your code and looks for ways to improve its performance without changing its functionality. For instance, it can eliminate redundant code, simplify calculations, and even rearrange instructions for better use of computer resources. Optimization is crucial for creating software that runs smoothly and efficiently, especially for resource-intensive applications. Section 6. From code to executable. The final transformation. Finally, after all the analysis and optimization, the compiler translates your code into machine language. This is the language that the computer's processor can understand and execute. The result is an executable file, ready to be run on your computer. Think of it like this. You've written a recipe in English, and the compiler has translated it into a series of precise instructions that a cooking robot can understand and execute to prepare your dish. The executable file is like that set of instructions for the computer. Section 7. The compiler's legacy, shaping the future of programming. Compilers have had a profound impact on the world of programming and technology as a whole. From the early days of computing, where programming was a laborious task involving punch cards and machine code, compilers have revolutionized the way we write and understand code. They have made programming accessible to a wider audience, leading to an explosion of software development and innovation. Today, anyone with a computer and an internet connection can learn to code, thanks to the power of compilers. From the apps on our phones, to the software powering self-driving cars, compilers are everywhere. They translate high-level programming languages into machine code, enabling our devices to perform complex tasks seamlessly. As we venture further into the digital age, compilers will continue to play a vital role. They are the unsung heroes behind the scenes, ensuring that our software runs efficiently and effectively. They will enable us to develop even more sophisticated and complex software, pushing the boundaries of what's possible with technology. Imagine the possibilities: advanced artificial intelligence, quantum computing, and beyond. So the next time you use a computer or a smartphone, remember the magic of compilers working behind the scenes. They are the bridge between human creativity and machine execution. And that's the story of compilers. From their humble beginnings to their crucial role in modern technology, they have shaped the world of programming in ways we can only begin to imagine. Now that you've learned about these amazing tools, why not explore further? Dive into the history of compilers, understand their evolution, and appreciate their impact on the tech industry. Research different types of compilers, from just-in-time compilers to ahead-of-time compilers, and see how they differ in their approach and efficiency. Learn about programming language design and how compilers are tailored to optimize specific languages for performance and usability. Or even try writing your own simple compiler. It's a challenging but rewarding experience that will deepen your understanding of how software works. The world of coding is vast and full of exciting discoveries waiting to be made. So, keep exploring, keep learning, and continue to shape the future of programming.